Hello, welcome again. We are studying the subject compressible fluid flow for civil services MECH, IFS and GATE Aerospace exam. And in this subject, we are studying oblique shock, and we have covered some theory parts. Now we'll solve some numerical based on oblique shock. First example is a uniform supersonic stream with m1 is equal to 3, p1 is equal to 1 atmosphere, T1 is equal to 288 Kelvin encounters a compression corner which deflects the stream by an angle theta is equal to 20 degree. Calculate the shock wave angle and P2, T2, M2, P02 and T02 behind the shock wave. So first of all, this is your Mach number m is equal to 3, initial Mach number, and initial pressure is 1 atmosphere and temperature is 28 Kelvin. And for m is equal to 3, initial Mach number, so this is your theta beta chart. This is your beta shock wave angle, here is this theta, and this is your theta deflection angle, this is your deflection angle, here it is represented by delta, and these are the Mach number. So here our Mach number is 3.0, so this is your Mach number, and theta is your 20 degree, so this is the point, so this will be the point, and corresponding to that we can see that the beta is approximately 38, or here we have taken it as 37.8. He has used the formula. So from chart it can be taken as 38 degree. Okay. So now after finding out beta corresponding to m1 is equal to 3 and theta is equal to 20, we can find out normal Mach number up behind before shock or upstream the shock. So that is mn1 is equal to m1 sin beta. m1 is 3 and beta is 37.8, and that is 1.839 mn1. So this is your normal shock number. Okay, and now corresponding to this normal shock number, we will see the table and see the shock table, and that has come out as 1.839. So that is your 1.839. This is your normal shock table, and this is the normal shock table, and this is Mach number, this is the pressure ratio, this is density ratio, this is temperature ratio, this is stagnation pressure ratio, and this is P02 by P1, and this is your M2. So and here our Mach number is N1 is 1.83, so that will be corresponding to in between this 1.8, this is 0.1820 plus 01 means 10 power 1, so it is 1.820, and this is 1.840, and corresponding to these two, or average of these properties can be seen from the table. So first is your P2 by P1, then T2 by T1, then P02 by P1, and this is your M2, and we have noted down these properties. So that P2 by P1 is your 3.783, and T2 by T1 is 1.562, and P02 by P1 is your 0.7948, and M2 after shock is 0.607. So here you can see that, we can see all the properties, just we are seeing here M2 only 1.83, 1.83, that is your it is approximately 0.6078, or here we have taken 0.604, okay, and stagnation pressure ratio is your 0.7948. And now initial pressure is given, that is 1 atmosphere, temperature is given to 88 Kelvin, and uh, from this we can calculate final pressure after shock, that is P2 and T2. So that comes out as 3.783 and 449.9 Kelvin. And from Mn2, using this formula we can calculate downstream Mach number also. This is normal Mach number downstream the shock. This is the actual Mach number. If we divide Mn2 by sine beta minus theta, that will give M2, and beta is your 37.8 and theta is your 20. So M2 will come out as 1.988. Okay. So now initial Mach number was 3, and corresponding to this initial Mach number, we from the isentropic table we can see the stagnation temperature to static temperature ratio and stagnation pressure to static pressure ratio. So this is so we'll use isentropic table corresponding to 3. So this is your isentropic table, and this is corresponding to 3 Mach number. This is the 3. Okay. And this series, these are the pressure ratio, temperature ratio, density ratio, and we can note down this stagnation pressure to static pressure, stagnation temperature to static temperature. So we can note down this corresponding to 3 and find out stagnation pressure and stagnation temperature. So that is your find out stagnation. First we can find out P01, and then we can find out P02 also, because we have P02 by P01 ratio also from this. Okay. Or we can directly find out P02 by multiplying and divided by P01 and multiplying and divided by P1. P1 is known, so P02 will come out as 29.19 atmosphere. And similarly T01 or T02 will come, we can calculate, because both will be same across shock. The stagnation temperature remains constant, so T01 by T1 into T1 is your T02 or T01, that is your 806.2.